Okay, so we are at section 2.36, talking about Bayesian inference for the Gaussian. So previously, in the previous section, we were talking about maximum likelihood inference, and now we're going to talk about Bayesian inference. And so what that's all about is introducing a prior distribution. So doing your estimation, not just for the likelihood, but combining the prior in there as well. Now, the structure of this section is, I think it's quite cool. I think what he'll do is, so first we're working with the Gaussian, which makes our life easy, but we're going to start by doing the Bayesian estimation for the mean. So that's what the first section is all about. Then we're going to do the Bayesian estimation. So we're going to assume the variance is known. We're doing the mean. That'll take us up to here. Then the next section, the next part is about, suppose that you know the mean and you want to infer the precision, so the 1 over the variance, because it's easier that way. And you'll see it's kind of the same general approach. And then finally, we'll talk about how to do both. So suppose that you don't know the mean or the variance. How to, what things look like in that setting. So that's over here. And then it finally finishes with just touching on kind of what things look like in the more, slightly more general setting. So the way I'm going to do it is I'm going to actually do this section in 3 parts. I'll start with the mean in this video, and then I'll do another video on the precision, and then we'll do one video on doing both. And they'll be kind of slightly shorter videos, but I think the ideas are kind of quite interesting, and I think they'll just be fun to go through them in those bite-sized chunks. So this time we'll just talk about how to do Bayesian estimation of the mean. Okay, so let's go. And there's some cool ideas here, I think, which are worth. You see, I've highlighted this entire section, so I think it's worth going a little bit more slowly through this to see what's going on. Okay, so let's get started. Okay, so maximum likelihood framework gave point estimates for the parameters mu and sigma, and so the idea was we just got one value. The Bayesian approach allows us to kind of preserve our uncertainty, so to have what's our confidence on that. And the idea is that we introduce a prior distribution, we update that with our observations. And in all of what we're going to talk about today, those observations are going to be independent and identically distributed. That's going to make the form of the equations really simple and really kind of insightful. So let us begin with a simple example in which we consider a single Gaussian random variable. We shall suppose that the variance sigma squared is known, and we consider the task of inferring the mean given a set of n observations. The likelihood function, so that's the probability of the observed data mu, given as a function of mu, is given by this. So what do we have here? Well, because our observations are IID, the probability of the data is the product of the probability of the individual data points. And so we get here, I hope you're used to this by now, we're getting a product of n Gaussians. And so you've got the n showing up here, the capital N. There's the variance, which we assume is known. And then each of the data points is showing up there inside this sum. So the exponentials are multiplying. We get a sum inside the exponential. And then that's what we have to work with. Again, it's really important to emphasize, I think it's good that he does it, that P of x given mu is not a probability distribution over mu, and it's not normalized. So it's a probability distribution over your data, but it's not a probability distribution over mu. So I mean, it will be positive, but if you integrate it, it's not necessarily going to come out to being 1. Not normalized. Okay, so this is the likelihood. Okay, so now the question is, we want to bring in a prior. What sort of prior should we bring in? And these days, these days, and kind of in general, the priors that you're going to bring in are going to depend on the problem you're working on. You might have prior information about what the distribution of the means would look like if you had no data. And these days we have really powerful computational tools that allow us to work with priors and do kind of numerically do all this Bayesian inference stuff. So we don't have to actually worry about the stuff we're going to worry about here, which is using a particular type of prior, which is the conjugate priors. And they're going to be conjugate because when you combine them with the likelihoods of a particular form, the posterior will have the same form, but with just different parameters. The whole game becomes, you'll just see how those parameters are updated. And that can be, in many settings it's not realistic, but it's, I think, really insightful because you can kind of see, how your parameters change as you observe more data. And that can be kind of really useful and can also give you insight into what's going on in settings where, okay, you don't have a conjugate prior, so things are really complicated. You have to do things numerically, but it can kind of give you some insight into what things should be happening. So I think it's just useful in that sense as well. Okay, so if we choose a prior p of mu given by Gaussian, it will be a conjugate distribution for this likelihood function. So let me underline this, a conjugate distribution for this likelihood function, right? Because we have, and the reason why is because the corresponding posterior will be a product of two exponentials of quadratic functions of mu, and hence will also be Gaussian. So essentially he's saying is, look, we're normally, when we often think about this as a kind of function of, of the data, but it's actually also a function of mu, and it's a quadratic function of mu. And now if we multiply with another quadratic function of mu, if it's assuming this is well behaved, so you remember you have to check not just any quadratic function, but most of the time what you work with, the quadratic function you work with will multiply and will all be positive. They'll all be positive, positive definite, and so all their eigenvalues, we won't get into that. But either way, so he said if we're multiplying two of these, if we're multiplying Gaussians that are, if we're multiplying a function that's quadratic in mu, we're multiplying with another function that's quadratic in mu, then chances are very good that well, the result will be quadratic in mu, and those the coefficient of that quadratic will correspond to variances of a Gaussian distribution. So in almost every case you work with, that will be the case. So the corresponding posterior will be a product of two exponentials of quadratic functions, and hence will also be Gaussian. So that's kind of the hence is almost always, but not necessarily always, but almost always the case. We therefore take our posterior distribution to be so and so. I just want to say, for example, very simple setting where it might not be the case is, for example, if you've got, suppose that this is, your data is just this, right? So this is your probability on x. Well, this is not going to be a Gaussian distribution, right? Because you need to have a negative sign on this. So, it's important that this is still a quadratic function with the plus, still a quadratic function on x, but the variance term doesn't have the right sign. So you just have to be kind of careful about things like that. We'll see more of that later. It'll become more clear. But yeah, I just want to kind of take a slight issue with the hence. So it's not always, but in almost every case we work with, if you're multiplying two quadratics, things will be well behaved. And certainly, so we therefore take our prior distribution to be also a Gaussian. So now we have prior distribution on mu, so mu now is the variable, and we have these hyperparameters mu naught and sigma squared naught, which tell us, what is the prior on the mean. So now we just say, well, this is by Bayes' rule, the posterior distribution is given by, so the posterior on mu, so we're interested in estimating mu, is proportional to the likelihood, which has this particular form, times the prior. And you should actually do this exercise, exercise 2.38, but you should be able to show that by just completing the square, we've already done this before, that the posterior distribution is now given by, so check it out, so we went from this prior, and now we have a posterior, right? So because of the way we chose our prior, and because of the way our likelihood looked, because we chose the conjugate prior to that likelihood, our posterior looks like it's the same kind of thing as our prior, but with different parameters. So let me just kind of draw these arrows, right? So you're in the same family, but it's just you've updated the mean and the variance. And the mean and variance update in actually a really cool way, really insightful way. So let's have a look at that. So and remember, this is our, so you have to be careful here. So what is the mean and variance we're talking about? So this is the mean of our estimate of the mean, and this is our variance of our estimate of the mean. So you see, you have to kind of keep things straight. So we're trying to estimate the mean. So now, so in addition to the maximum, so the maximum likelihood setting will just tell us, well, the mean is this. But now we have a distribution over what that mean value is. And that distribution is determined by, in our case, it's really well behaved. It's a Gaussian with a particular mean and a variance. And we started out with a particular mean there and a variance. And now, given the observations we have, we've updated those means and the variances. And how have we updated them? So let me erase this because it's a little bit distracting. Okay, so check it out. So what do we have? So we've got that the mean of our estimate looks like, so it's a combination, so it's mu naught, so that's our prior, times the maximum likelihood estimate. So it's kind of it's a balance between the our prior mean and the estimate you would get if there was no prior. You just use the maximum likelihood. And the variance is actually easier to talk about in terms of the precision. So the precision of your estimate is the sum of your prior precision and and the precisions contributed by your data points. So that's what he's basically going to say. And I think it's really, I've highlighted everything here because it's all actually quite important. So in which mu-ml is, since mu-ml is the maximum likelihood solution given by the sample mean. So you see, now our estimate of the mean is not just the maximum likelihood estimate, but it's actually, it's depending if you have, we'll talk about if you have lots of data, it will tend towards maximum likelihood estimate, but it also has some contribution from the prior. And same with your precision. So now let's have a look and see what we've got here. Okay, we're spending a moment studying the form of the posterior mean and variance. First of all, we know the mean of the posterior distribution, so this thing, given by that, is a compromise between the prior mean and the maximum likelihood solution. So let me just highlight those. So it's a compromise between the prior mean and the maximum likelihood solution mean. Okay, so, and this is actually a useful thing you should always do when you do these things. See what happens when you take different limits. So he's going to do that. So it's very good practice to make sure your algorithm is behaving the right way. If the number of observed data points n equals 0, then 2.141 reduces to the prior mean as expected, right? So if you don't have any data points, well then this disappears, and you just get the prior mean. That makes sense, right? You have no observations, you should fall back on the prior. Now, if you get infinite amounts of data points, well, what's going to happen? So this is going to go to 0, so that's going to be gone, and this is just going to become 1. So you're going to just get mu-ml showing up. So the point of that is that if you have tons of data, the prior should essentially, the influence of the prior should disappear. So for the posterior mean is given by the maximum likelihood solution. And now, okay, let's look at what's happening for the variance. We see that this is, so we're now most naturally expressed in terms of the inverse variance, which is called the precision. We've already met the precision before. Furthermore, the precisions are additive, so that the precision of the posterior is given by the precision of the prior, so that plus one contribution of the data precision from each observed data point. So that's kind of pretty cool as well, right? Because you can write this as plus sigma squared plus 1 over sigma squared n times. So each one of your data points is contributing one term to the precision. So the more each time you see a data point, you get a little bit, your estimate gets narrower and narrower. And and that's pretty cool. And it seems to not depend on the value of the mean. So it seems like whatever you observe, your variance will shrink. Right. Okay. Okay. The precision steadily. Yeah. Right. So as we increase the number of observed data points, the precision steadily increases, corresponding to a posterior distribution with steadily decreasing variance. With no observed data points, we have the prior variance. So if n is 0, we just get the original variance that we had. Whereas if the number of data points goes to infinity, the variance goes to 0, and the posterior distribution becomes infinitely peaked around maximum likelihood solution. So the idea is as this goes to 0, as n goes to infinity, precision goes to infinity, variance goes to 0, you get a very sharp peak. It just says, look, I've seen so much data, I know exactly what the mean is. And you get infinitely peaked around the maximum likelihood solution. So we therefore see that the maximum likelihood result of a point estimate for mu, given by this, is recovered precisely from the Bayesian formalism in the limit of an infinite number of observations. Okay, so in some sense you could think of the ML solutions like what you would get if you just had an infinite number of observations, and it's a point estimate because there is no variance. It's ML says, oh, I know exactly what it is. Because we have an infinite amount of data. So it's kind of like doing ML maximum likelihood estimation. It's like imagining you have infinite amounts of data. In this case, you don't, and you have error bars, but they're just 0. Okay. Right. And it's also cool. So now for finite n, if we take the limit as if the prior variance goes to infinite, so essentially you're saying I have more and more uncertainty. So in which the prior has infinite variance and the posterior mean reduces to the maximum likelihood result. So it says that you can kind of get there in another way, right? So if you just set the prior variance to infinite, so this becomes infinite, then this goes to 0, and these two combine, and you still get the maximum likelihood. So it's kind of like there's two ways of getting the maximum likelihood result. You can either get it by getting infinite data, or if your variance is if your prior is completely flat. Sometimes you call that a uniform prior or an uninformative prior. So if you don't have any, if your prior doesn't tell you anything about your parameter, well, then your estimate will be your maximum likelihood estimate. While the posterior variance is given by sigma n squared is equal to sigma squared. So what is going to be the posterior, while from 2.142, the posterior variance given by sigma squared n is equal to sigma squared over n. That's right, yeah, because as this goes to infinity, all you get is that. So your variance just shrinks. So there's no contribution of the prior terms of the variance, it just shrinks. Yeah, okay, so one thing I wanted to say is, so there's actually so obviously these formulas are correct. One thing I want to point out is actually a nice way of looking at these results, and I'm sure obviously he knows it. I'm surprised he didn't mention it. And if you can just think of this as, instead of thinking of this as these expressions in terms of these variances, and he already kind of gave us the hint that it actually makes more sense to think about this in terms of precisions. And so if you actually write this equation in terms of precisions, you actually see that it's a precision weighted mean of the two. So I think let's actually go and do that. So what we want to do first is we want to express the denominator here in terms of these precisions. Okay, so on the bottom, I want to get precisions showing up, and so then we'll figure out what we have to do to the top. So let's try doing that. So you guys can see this. Okay, good. So we can write this as, so this is going to be sigma squared plus n sigma 0 squared over sigma 0 squared. So I'm just, right? Okay, so that's that. So now if I see, so what do I have, and this is precisely what I have in the denominator. So I'm going to divide the denominators by sigma o squared sigma squared, and then if I do that, then I have to do the same thing to the numerators, right, to get the same expression. So let's do that. So I'm going to erase this, and I'm going to divide this by sigma 0 squared sigma squared, so the product of the prior and I'm going to do the same thing here. Let me get rid of that now. Oops. Okay, so there we go. Okay, and so now if we do that, well, then you can see that what's going to be left here, we're going to get, this is going to become, and we'll have to do the same thing on the top as well. Right, so what are we going to get on the top? Well, on the top, we're going to get 1 over sigma 0 squared over, and on the bottom, we're going to get what? We're going to get n over sigma squared plus 1 over sigma 0 squared. I'm going to get rid of all this stuff now. Plot, and then we still got the mu naught, right? Because we divided the top and the bottom by the same thing. Plus, now what do we get on this side? Well, we're going to get n over sigma squared over, again, the bottom is the same. And it's going to be mu ml. Okay. So why do we do all that? So let's just call this, let's just define this as, we're going to call this as the overall variance, the overall precision. And actually, well, let's just write that as, we'll call this as 0 plus let's say n times the variance of the data. We'll call the variance of the data lambda. Okay, so then what does our expression become? Well, our expression then becomes, just running out of space, but so then this thing is going to become, in our new way of writing, it's going to be, so that top thing, this is just mu naught. So mu naught times mu naught over mu naught times n mu. Sorry, what am I calling it? They're lambdas. plus n lambda over mu naught plus n lambda mu ml. Okay, so that's the thing. So let me, now that we have that, let me just erase all of this and just write that on top in big letters. So this is going to equal to, so you see on the bottom we have the total precision. So let's get rid of all of this stuff. So that's kind of what I wanted to focus on. So you see we have a precision weighted. Notice that, so the thing to notice is that, notice that this plus this is equal to 1. Same as here, so nothing changed. But now you have kind of a linear, a linear weighting between the two, right? So it's like you can actually think of this as, here is mu naught at some other point in mu ml, and now your estimate is actually going to be somewhere along this point, and where it is along this point is going to be determined by that fraction. So you're going to say, well, I'm going to be, so this point here is, so this point here is going to be, you know, mu now, oops. Let's actually call this, for example, we can call this, I don't know, let's call this alpha. So then this thing is going to become 1 minus alpha. So this is alpha mu naught plus 1 minus alpha mu ml. So you know, as alpha when alpha becomes 0, then that means that your n is gone to infinity. So you've got tons of data. It starts shifting to that side. When alpha goes towards 1, that means that you're kind of weighted towards your prior, and you're shifting towards you know, your data points have gone to 0, and you're shifting towards your prior. It might make more sense to define, you know, alpha and 1 minus alpha the other way. But the whole point is that you're going to be doing, you're just going to be going on a sliding scale between mu naught and mu ml. The weighting is going to be determined by the precision. So if you're, you know, if you have lots of data, then the precision of, you know, contribution of your data point is going to be really large, right? It's going to be, you know, n mu. That's going to be very large relative to the prior. Whereas if you have very small, then few data points, then you're going to be weighted more towards the prior. And so as you add more data points, you start kind of, this alpha starts going more towards 0, I guess, or however you want to describe it. And your data point starts shifting more in that direction. So yeah, I just want to say, yeah, my main point here was that you're getting, you know, it can be a little bit mysterious, you know, what these numbers mean, but just think of it as a precision weighted combination. And the precisions that you're getting are, one is coming from your prior, and then one you're getting from your data. And you just weight them both by their corresponding precisions, and then you divide by the sum precision, by the total precision. That's what you have. That's what you have here, and that gives you the answer. So hopefully that gave you an additional kind of little bit of insight into what's happening. Great. Cool. Yeah. Okay. Let's look at this picture. I think it's a cool picture of what this actually looks like. So what do we have? You guys can see. Okay, so the idea is that we have a prior distribution on mu, and in this particular case, we're told that the mean is 0.8 and a variance of 0.1. So and we know what that is, and so we just keep getting data that's coming from a mean of 0.8. And after one data point, you think things shift over. After 2, they're shifting over even more. By the time you have 10 data points, well, 2 things have happened. A, things have really kind of tend to focus around 0.8 because that data is starting to dominate, and the distribution is getting narrower. And if you get more and more data points, this distribution is going to get narrower and narrower and narrower around 0.8, because now you have so much evidence that the mean really is 0.8. So it's kind of a, you know, nice picture of what the situation looks like in a very simple setting. Your mean is moving, and you're getting, and the cool thing, look, is that you also have a distribution, right? So you have some uncertainty, which is really cool, right? Like after 2 data points, you know, maximum likelihood will just tell you, well, this is, you know, well, actually, maximum likelihood it wouldn't actually even be influenced by the prior, so it would probably even shifted more towards that side. But either way, it would just give you the point, the maximum point of this curve. Whereas now we actually get some uncertainty, and that can be really useful if you're like making decisions, right? Like if you're making decisions about, if that's going to the yield on some stock or something like that. Well, you want to know that, okay, how much uncertainty you have whether to make your decision. So yeah, so that's kind of a cool, very useful picture to look at about what the situation looks like. Generalization as a result to a d-dimensional Gaussian random variable is straightforward. So exercise 2.40, have a go at that. I'm sure it'll be an easy one. Okay, now we have, so now the next little bit is also actually really useful. So that, in its own way. So I thought, obviously, worth talking about. So we have already seen how the maximum likelihood expression for the mean of a Gaussian can be recast as a sequential update formula in which the mean after observing n data points was expressed in terms of the mean after observing n minus 1 plus the contribution from data point x of n. Okay, so that's what we did in sequential estimation. That was the last video. Now, the Bayesian paradigm leads very naturally to a sequential view of the inference problem. And this is cool. This is very general. To see this in the context of the inference of the mean, so let's write the posterior distribution with the contribution from the final data point separated out. Okay, so all we've done here is, remember what we've done? We've got the prior term, and then we had one term multiplying for each of the data points. So there's n minus 1, and there's the nth one. And all we've done is we've just separated those contributions into the contributions of the first n minus 1, combined those with the prior, and now the latest contribution. And the reason why we've combined that is that, so this is just the posterior distribution after n minus 1 data points, and we can see that this can be also viewed as a prior distribution, right? So this is the cool thing. So can be viewed as a prior distribution, right? So it's like after you've seen n minus 1 data points and you combine them with your prior, and now you've got this posterior distribution. Well, now you can view that posterior as itself a prior for your next data point. So that's like a really cool, I think, really beautiful idea of just. I think one of the really nice advantages of the Bayesian approach of how natural it is to combine data to bring new data points in, and you just get these really nice algorithms just showing up. Okay, we see that this can be viewed. We see that this can be viewed as a prior. Sorry, laser pointer. As a prior distribution, which is combined using Bayes' theorem with the likelihood function associated with data point x of n. So that's this one, to arrive at the posterior distribution after observing n data points. So that'll be what comes out of this whole process. So that's the posterior distribution after that many data points. This sequential view of Bayesian inference is very general and applies to any problem in which the observed data are assumed to be independent and identically distributed, right? And actually, I think the key thing actually we're even using here is it's not even, you don't need them to be identically distributed. All we need here is independence, right? That's all we've used. The fact that we can just separate out the probability of the data into the prior times the probabilities of the observations. And so the reason why we can do this separation is because of the independence assumption, that the probability of, I'm sure you remember this, the probability of, x, 1 to xn given mu by independence, this was just equal to p xi, given mu. I is equal to 1 to n. And the point is, these p's for the different i's, they could actually be different. They don't have to be identically distributed for this approach to work. But it's kind of the nicest setting of it is when they are. And often they will be like, there's often no reason to assume that the distribution from which the data points are coming is going to be changing very rapidly. It does happen, certainly, but it's often a good first guess anyway, that it's always the same. The sequential view, yeah, very general. Okay, cool. So I think good. So I think that's a good place to stop. I think it was a pretty simple section, but I think some really important ideas, and I think this particular, this is really important. Just remembering this is really important, really insightful. Trying to remember, what's happening to the mean, what's happening to the precision. In most, in many other cases, it's not going to be as clean as this, but I think just trying to think about what's happening in this Gaussian case with the mean shifting, the variance getting sharper. I think they kind of give you some insight, some intuition into what's happening in more complicated situations. So I think that's it for this section. I think we'll continue next time with another short section on the variance, and then with when you don't know both the mean and the variance. So hopefully it was useful, and that hope to see you next time. Thank you.